Recall that in the last chapter we talked about the binomial distribution. In this segment, we want to describe certain conditions under which the binomial distribution and problems involving a binomial distribution can be accurately approximated by using the normal distribution. And now that we're familiar with using the normal distribution, it may turn out that those calculations are a little bit easier than having to go through the calculations for the binomial distribution. Consider this. Now remember, with the binomial distribution, n was the number of trials, r the number of successes, p the probability of success, q the probability of failure. Now in our situation here, let us suppose that n, the number of trials, is 25. The probability of success is 0.25, and we want to find the probability that r is greater than or equal to 8. Now, from our previous experience, there are a couple of ways of doing that. One way is to calculate the probability that r is 8 and add the probability that r is 9 and add the probability that r is 10 and so on, all the way out to adding the probability that r is 25. Another way is to calculate 1 minus the probability that r is less than 8. This would probably be the way that we would decide to do this kind of problem right now. Okay, now it turns out that a problem like this can be approximated using the normal distribution. And these are the circumstances under which the approximation becomes accurate. And those circumstances are these: that when n, the number of trials, times p, the probability of success, is greater than 5, and nq is also greater than 5. We'll use the normal distribution. Now for this problem, np is 25 times 0.25 or 6.25. nq is 25 times 0.75 or 18.75. So we meet the criteria then for using the normal distribution to approximate the binomial distribution. Now, here's how we start the process. We want to calculate mean and standard deviation. Those are very important features involved in using the normal distribution. So calculating the mean and standard deviation using information from the binomial distribution means that the mean is np, or 25 times 0.25, 6.25. The standard deviation is the square root of npq, which is the root of 25 times 0.25 times 0.75, or approximately 2.17. Now it would seem at this point that we're thinking, okay, we're outlining our problem here. This is the mean and standard deviation we're going to use in the normal distribution. That's fine. And for the problem here, we were talking about the probability that r, the number of successes, is greater than or equal to 8. And it would seem that what we're going to calculate using the normal distribution is an x that's greater than or equal to 8. But not quite. Not quite, because let's look at areas involved with the graph of a normal distribution and the graph of the binomial distribution. Now remember, the graph involved with a binomial distribution was a histogram. And here's a histogram corresponding with the situation we have at hand. Now this is just part of the graph. The graph extends a little bit in this direction and quite a bit in that direction. But these are probabilities associated with each of these values in the distribution. 6 has a probability of roughly 0.18. Okay. Now what we're trying to do, because we are thinking in terms of areas, is this. Areas correspond with probabilities, and we're thinking about adding all of these areas and out to the right. Now when we sort of mentally overlay a normal distribution on top of this binomial distribution, it looks about like this. Now I'm just going to try to hit the midpoints of the tops of these just to kind of emulate the situation, and it would look kind of like I'm trying to make this look like a normal, something like that. Well, roughly like that. But notice that if I'm thinking about area involved with this normal distribution, do I want area starting here at 8 and going out to the right? No, I don't want just that area. I want to also include the remaining portion in this region. You see, I don't want just half of that histogram. I want the whole histogram if I'm going out here to the right of 8. So I want to take the shoulder of this histogram. I want to go between the one before and the one that I want to be involved in, and so I want to use 7.5. And that's the only trick. That's the hitch in this whole get-along. We have to make sure that now sometimes this will be a thing where we want to include a value on one side or another. Sometimes we want to exclude a value. It depends on whether it's greater than, less than, and so forth. Intuitively, you'll sort of understand, you'll know what that is. That if we want to include, if we're talking greater than or equal to 8, then we want everything that is involved with 8 in the binomial distribution, and that stretches all the way back to 7.5. So that's why we're using a 7.5 figure in the calculation for the normal distribution. Okay, let's review just a little bit. Binomial distribution, normal distribution. Under the binomial distribution, we had 25 trials, probability of success. We're looking for the probability that our successes is greater than or equal to 8. We go about the business of calculating mean and standard deviation. Good, we've already done those things. Then, when we jump over to the normal distribution, we use the mean and standard deviation that we calculated here, but we're finding the probability that our x value in our normal distribution is greater than or equal to 7.5, because we're thinking of these histograms over here for this binomial distribution, and we want to capture all of that histogram involving 8, and it stretches all the way back to 7.5. Okay, so we want x to be greater than or equal to 7.5, and away we go with what we know about the normal distribution. That is, z is x minus mu over sigma, so we have 7.5 minus 6.25 over 2.17, which is 0.58. So a z then of 0.58 is what we're talking about. We would sketch the situation. So we sketch it here. So we want the area under the curve that's to the right of 0.58. Oh, how do we do that? Well, we find all of this area, 0.5, and we subtract the area up to this point, which involves using the table. So all the area on the right, that's 0.5. The area 0 to 0.58 turns out to be 0.2190 from the table. Subtracting here, we get 0.281, and the probability then that r is greater than or equal to 8 from that binomial distribution is approximately 0.281. Let's take a quick look at the calculation using the table in the back of the text, which is a left tail style table. The general idea is to take the total area under the curve and then subtract the area which is to the left of 0.58 because that's the value that's in the back of the text, and then we'll be left with the area which is to the right of 0.58. Well, the area under the curve is 1, and the area to the left of 0.58 from the table is 0.7190, and the difference is 0.281 as expected. Now the exact value on this turns out to be 0.2735, you see, but we're within sort of 1% of the actual value by using an approximation within the normal distribution. Pretty neat trick, isn't it? USA Today reported that 11% of all books sold are romance-oriented. If a local bookstore sells 316 books on a given day, what is the probability that less than 40 are romances? Before we even begin to answer the question, let's outline some information here. We know that if we're talking about 316 books being sold on a given day, that's what the N value is for our problem. And incidentally, we're in a section involving a binomial distribution and the idea that the normal distribution can emulate the binomial distribution under certain circumstances. So we know we have a binomial probability distribution here. We're talking about the probability that a randomly selected book sold at this bookstore is going to be a romance to be 11%. So the p-value is 11% or 0.11. The q-value is easily calculated as 1 minus p. 1 minus 0.11 is 0.89. So q is 0.89. And now from here we can calculate a mean and standard deviation. Remember, the mean is NP, So that's 316 times 0.11, or 34.76. The standard deviation is the square root of NPQ, which turns out to be this rather lengthy looking decimal. And we're going to use this long-winded version of the standard deviation for accuracy purposes. That is, if we used a rounded version, then we're using a version which has more error built into it. And if we use a rounded version, we are likely to get a rounding error for our answer. So we want as much accuracy as we can in making the initial calculations or the various calculations in our problems. Okay, let's find the probability that less than 40 of these books sold are romances. Now we begin the idea with the binomial distribution associated with this problem. Now notice that at the bottom these are some numbers of books, and the bars above those numbers of books correspond with the probability associated with that number of books being sold, that number of romances being sold. So we understand that under certain circumstances, that is, the circumstance that NP is greater than 5 and NQ is greater than 5, under those circumstances a normal distribution will emulate this binomial distribution. So we can think about the normal distribution overlaying the binomial distribution. Now here is the probability associated with exactly 40 romance novels being sold out of this 316 total number of books being sold. Now we're talking about, though, the probability that less than 40 are romances. So we want to find the area that is to the left of 40. That is, we want this area under the curve. And we don't really want 40, you see, so we'll have to take that out. Now, I'm illustrating it this way to illustrate a point. We don't want the probability associated with 40 because we want the probability that less than 40 are romances. Now, so what value are we going to use for x when we use our normal distribution to approximate this binomial distribution? Well, we're going to use this value, this border between 40 and 39. And that border is 39.5. All right, so 39.5 is going to be a kind of a magic number here for us in just a moment. Well, here's how the calculation is made. We think about the probability that the number of romances is less than 40 is approximated by, it's approximately, see, we're jumping into our normal distribution here. It's the probability that an x in the normal distribution is less than 39.5. And we'll calculate a z associated with this 39.5 like this, and remember the mean and standard deviation are given above, so we pop in an x of 39.5 and make the calculation to find the z value to be 0.85. Now with this 0.85 then we understand that our probability then is the probability that the z is less than 0.85. So we turn to the table and find that a z corresponding with an area of less than 0.85 is 0.8023. And this is the probability then that less than 40 of these books that are sold on this day are romances. Let's calculate the probability that at least 25 are romances. We'll start the way we did before with our distributions kind of overlaid, our binomial distribution and normal distribution overlaid with one another. And here is the position that exactly 25 romances are sold. And we want the probability that at least 25, that's 25 or more. So we want the area under the curve corresponding with all of this area. Now notice that since we want to include 25 as part of the region that we're calculating, we're going to use the sort of the left-hand border of 25, and that's the border that's between 24 and 25. So our x is going to be 24.5. So again, we think of it like this. The probability that the number of romances is greater than or equal to 25 is approximately the same as the probability that an x in the normal distribution is greater than or equal to 24.5. Now here we're calculating the z associated with the 24.5, and that z is negative 1.84. So our probability that x is greater than or equal to 24.5 is the probability that z is greater than or equal to negative 1.84. But we know that our table contains information about area to the left of z-scores, so we're going to think of this as 1 minus the probability that z is less than negative 1.84. And the z corresponding with a negative 1.84 is 0.0329. And 1 minus 0.0329 is 0.9671 for the area. And that is the probability associated with at least 25 of those novels being romances. Now let's calculate the probability that between 25 and 40 are romances, including 25 and 40. So between 25 and 40, including 25 and 40. Well, here is the probability associated with exactly 25. Here's the probability associated with exactly 40. And we want all of these to add all of these probabilities between those two. Well, since we're including the 25 and the 40, we're going to use this left border of 25 and the right border for 40, you see, as sort of magic numbers when we're talking about our normal distribution. So the probability that the number of romances is between 25 and 40, including 25 and 40, is approximately the same as the probability that x is between 24.5 and 40.5, including those two. Now we need z-scores associated with those, and for 24.5 the calculation is made like this. So the z is negative 1.84. We calculated this earlier. And then for 40.5 we replace that x with 40.5, and we find the z associated with that to be 1.03. And we put that value into the inequality. Now we may recall that in finding the probability or the area, which is between two z values, we simply take the difference of the two. That is, we're going to take the area associated with the larger z-score and subtract the area associated with the small one. That's all there is to it. Now, z of 1.03 implies an area of 0.8485. A z of negative 1.84 from the table implies an area of 0.0329. Taking the difference, we find the probability, or the area, to be 0.8156. Last part of the problem says, in the solution to this problem, what was n, p, q? Well, we calculated those earlier. Does it appear that both np and nq are larger than 5? Why is this an important consideration? Well, here were the np and q that we calculated earlier, and if we punch our calculator and calculate np and nq, we get these values. And those values were important, recall, because they allowed us to transition from the binomial distribution to the normal distribution. That is, these conditions assure us that the normal approximation will be sufficiently close to the binomial probability for most purposes.